We are going to solve problem number 13 right now. They're asking what value of magnetic field would make a beam of electrons traveling to the right at a speed of 1 times 10 to the 6 meters per second. We'll write that down. So velocity equals 1,000,000 meters per second. 1 times 10 to the 6 meters per second. Go undeflected through a region where there is a uniform electric field of 900 volts per meter pointing vertically up. So our electric field they give us is 900 volts per meter. And this is directed upwards. Okay, and the velocity, I should write an arrow right here. This was going to the right. So we are going to create a magnetic field that is going to basically oppose this electric field in one sense of the word. So if we have an electric field pointing upwards, we'll draw this going up, and we have a negative particle that is entering here. The negative particle is going to feel a force due to the electric field. And that's actually, one way of thinking about it, that we're aware that there's an electric field because charged particles will feel a force on them. The force that they'll feel is given by, force in an electric field is given by QE, where Q is the charge of whatever this charged particle might be. It might be a proton, an electron, it could be a charged dust particle, and E is the strength of the electric field. We recall that electric field lines are drawn from positive to negative. That's the way that they like to flow. So it's as if we have a bunch of positive charges down here on the bottom and a bunch of negatives up on the top. Well, a negative charge is going to want to go towards positive, which means it's going to feel a force downwards. So without any magnetic field, it would go straight and curve down and eventually crash down to wherever these objects are that are creating our electric field. So we're feeling a force, a pull or a push downwards due to the electric field. This means that if it's going to go undeflected, we have to have a magnetic field that's going to push this particle upwards. The force that we have for the magnetic field on a moving charged particle is given by QVB sine theta, where theta is the angle between the particle's velocity and the magnetic field. These are going to be perpendicular, so theta is going to equal 90, which means sine of 90 is 1, so we'll just say QVB for now. Now, what direction would we have to have this magnetic field pointing? You choose right hand or left hand. It's going to be left hand because it's a negative particle. Remember, for the right hand rule, we use our right hand for currents or the flow of positive charge, which, thank you, Ben Franklin, used to think that currents were due to the flow of positive charge. Thus, we're kind of stuck with conventional current being backwards from what the real flow is, which is actually electrons. That's what electricity is. But when we talk about conventional current, we're talking about the flow of imaginary positive particles. Historical footnote aside, if you point your left hand's thumb to the right and your palm upwards towards the ceiling so that this particle is feeling pushed up, you'll see that your fingers, your index through pinky, are pointing back at you. So that means that's the direction of the magnetic field, which should be out of the board. So we'll denote that with a couple of dots. So now we've got part B answered. We've figured out the direction of the magnetic field. Let's figure out part A, what the strength of this magnetic field is. If the electric force is going to be balanced by the magnetic force that's pushing up, we can say FE equals FB. So real quickly, we can write FE equals FB and plug in our equations. So we said that would mean QE would equal QVB. Canceling our Q's out from both sides, we get that E over V equals our magnetic field. which in this case, if we've been told that our electric field is 900 volts per meter, and our speed is 1 times 10 to the 6 meters per second, that means the magnetic field that we need to have this particle pass through undeflected should be 9 times 10 to the minus 4 Tesla. Good number to hang on to. We will be using it in the next part. So hang on to this number, write it down on something good. Okay, so in part C, they ask what is the frequency of the circular orbit of the electron if the electric field is turned off? So the electric field is gone. We just have a particle in a magnetic field. If it's got a velocity and it's traveling normal, it will go in a circle. So if it were going in a circle, we have a certain force that's keeping us going in a circle, which we call the centripetal force. Fc, force centripetal, is given by mv squared over r. Now the question is, who plays the role of Fc? We've had many forces. A string could pull and it could be tension that would give us centripetal force, or we could have a car going around a curve where friction would play the centripetal force. In this case, it's due to the charge moving through the magnetic field, so QVB. So we'll say that mv squared over r equals QVB. This can be a little bit simplified, so we'll say that m over r times v equals q times b. You might be wondering now, how do we get to frequency? Or how do we get to period? Because you know that frequency and period are related. Frequency is the inverse of period, and vice versa. So recall that period is the time it takes you to, let's say, go around one loop. So for example, period, your, let's say, lap time around a track, would be 2 pi r, the circumference of the track, divided by v, your velocity, how fast you're going to run. We have v and r here, and we've got period. That's what we want, is period. Because if we take 1 over period, we get frequency. So we could write f equals v over 2 pi r. If we have v and r, we also have v and r in these equations right here, so we could solve this bottom equation for v or r and plug that into here and have an expression that we could solve for period or frequency. So let's go on ahead and say that, in this case, frequency equals v over 2 pi r, and we will solve for, let's say, radius. Doing that, we'd multiply the left side by r, and we would divide by frequency. So we can say that r equals v over 2 pi f. And now we can go and pop that into this equation. We need 1 over r for this equation up here, right? Because we're saying that it's mv divided by r. So 1 over r equals just the inverse of our expression here, 2 pi f over v. Now let's multiply by mv. So now we have mv, which equals qb. Solving for frequency, we say that frequency equals qb divided by 2 pi m. Notice that the v's cancel. We got a v down here and a v up here. So those canceled out. That's why v didn't get carried over. Plugging in your numbers for Q, we have an electron, so 1.6 times 10 to the minus 19. B, we have, I believe, is 9 times 10 to the minus 4 Tesla from part B that we calculated. We've got 2 pi, and we've got m, which is 9.11 times 10 to the minus 31 kilograms for an electron, yielding us a final answer of 25 times 10 to the 6th hertz, also known as 25 million hertz or 25 megahertz.